The main goal is to soften tap water using a nanofiltration module and then determining the water hardness by EDTA titrometric method. Specifically, the goal of the nanofiltration process is to soften the tap water distributed by the city of Montpellier, which comes from the Lez River. The experiment will be conducted using a micropilot membrane separation system equipped with a nanofiltration module manufactured by GE. The nominal conditions for the filtration process are a transmembrane pressure of 15 bars and a flow rate of 500 liters per hour. However, the transmembrane pressure can be adjusted between 10 and 25 bars to study the effect of operational parameters. The goal of the titration experiment is to determine the concentration of calcium and magnesium ions in the water, which defines the total water hardness. The titration will use a complexation reaction with EDTA, and the hardness will be expressed in French hydrometric degrees. When working in the separation processes lab, safety glasses are mandatory and contact lenses are forbidden. A cotton lab coat and protective gloves should also be worn. Pipettes must be used with a safety pipette filler. No smoking, eating, or drinking is allowed in the lab. Flasks containing strong acids or bases must remain under the hood. There are pictograms on all bottles indicating risk and safety. Do not pour any solution with a pictogram down the sink. Instead, use the marked recovery cans for solvents and aqueous solutions. Broken glass and used gloves should be disposed of in the designated box. The lab is equipped with a first aid pharmacy, safety shower with an emergency eye wash device, 2 fire extinguishers, toxicological sheets for different products, and soap and disinfectant dispensers. Emergency numbers are posted in the room and by the phones. There is also a punch on the electrical cabinet in case of electrocution. Report any safety problems to the lab staff. To soften tap water using the nanofiltration setup, begin by turning on the system and ensuring the drive display is lit. Select the organic circuit using valves VB101, VB102, and VB103, and closed drain valves VB01 and VB06. Fully open valve VR51 and fill the tank with cold tap water, ensuring both retentate and permeate outlets are directed to the tank to prevent the pump from running dry. Start pump PA1 and increase its speed until a flow rate of 500 liters per hour is achieved. Allow the pump to run until all air is expelled from the system through the retentate and permeate outlets. Next, increase the pressure to 15 bars by gradually closing the VR51 control valve. Continuously monitor and adjust the pressure and flow rate to maintain 500 liters per hour and 15 bars throughout the filtration process. Finally, collect the permeate in a separate container for analysis and observe any changes in the retentate. The goal of the titration is to determine the concentration of calcium and magnesium ions in water to calculate water hardness. This method uses a complexation reaction with ethylenediamine tetraacetate EDTA ions, denoted as Y4-. The titration is carried out at a pH of 10 using the disodium salt of EDTA to favor the complexation reactions. The EDTA complexes with calcium and magnesium ions are colorless, so areochrome black T, EBT, is used as an indicator. EBT forms colored complexes with calcium and magnesium ions that are less stable than the EDTA complexes. As EDTA is added, it gradually releases EBT until, at the equivalence point, all EBT is free in solution. This causes a color change from violet, EBT complexed with Ca2+, and Mg2+, to blue, free EBT in solution. To determine the water hardness using the EDTA tetrametric method, first introduce 10 milliliters of the water sample into a 100 milliliter Erlenmeyer flask. Then add 5 milliliters of ammonia buffer at pH 10 to the flask, followed by a micro spatula of areochrome black tea indicator. The solution will turn violet due to the complexation of EBT with calcium and magnesium ions. Next, titrate the solution with 0.01 molar EDTA solution from a burette until the solution turns from violet to blue, indicating the endpoint of the titration. This marks the point where all the calcium and magnesium ions have complexed with EDTA, and free EBT is present in the solution. It is recommended to perform a quick titration to get an approximate endpoint, followed by a more accurate titration to obtain precise results. Now, with all the measurements taken, we can now analyze and visualize our data. The permeate flow rate, which was weighed over a certain period of time, can be divided by the density, 1,000 grams per liter, to get it in terms of liters per hour. Then to get the flux, this value was divided by the cross-sectional area, which is 0.38 meters squared. These values were then plotted against the associated pressures of their measurements and visualized. This plot shows permeate flux in liters per meter squared per hour versus pressure, measured in bar. The line of best fit is linear with an R squared of 0.926. The slope of the line is the permeability of species through the membrane. Therefore, the permeability is 2.15 liters per meter squared per hour per bar. For the titration, concentration of the ions of calcium and magnesium were measured in each of the water types: mineral, tap, and filtrated. The following reaction occurs with calcium and magnesium with ETA, indicated by Y. We know the concentration of ETA to be 0.1 molar, so measuring the volume emptied from the pipette until a color change is observed and multiplying it by the known concentration can give us the amount of moles. Then we know that it is a 1-to-1 ratio of calcium and magnesium, so the moles of calcium and magnesium will be the same as those calculated for the ETA. These values are then divided by the total volume, which is 10 milliliters. The concentration of the calcium and magnesium ions ends up being 0.0024 molar, 0.0038 molar, and 0.0015 molar for the mineral, tap, and filtered water, respectively. From there, the hardness, degree TH, could be measured with the equation shown on the screen. With these values, there is an associated classification for the hardness of water. The hardness of mineral water was 24 degrees TH, corresponding to medium hard water. The hardness of tap was 38 degrees TH, so it was very hard water. Lastly, the filtrated water had a value 15 degrees TH, corresponding with a soft classification. Given that AOTH is equivalent to 4 milligrams of calcium per liter and 2.4 milligrams of magnesium per liter of water, the values previously calculated can be multiplied by these values to get the concentration of Ca2+ and Mg2+ in each of these water types. The mineral water had a concentration of 96 milligrams per liter of calcium and 57.6 milligrams per liter of magnesium. Its conductivity was measured to be 456 millisiemens per centimeter. The tap water had a concentration of 152 milligrams per liter of calcium and 91.2 milligrams per liter of magnesium. Its conductivity was measured to be 781 millisiemens per centimeter. The filtered water had a concentration of 60 milligrams per liter of calcium and 36 milligrams per liter of magnesium. Its conductivity was measured to be 376 millisiemens per centimeter. We can now analyze these results. For the nanofiltration experiment, the plot shows a clear linear relationship between the flux and the pressure. The high ER squared of 0.92 indicates consistent behavior. The permeability, 2.15 liters per square meter per hour per bar, indicates how easily the species passes through the membrane under pressure. Now for the titration results, the concentrations of calcium and magnesium ions in 3 different types of water, mineral, tap, and filtered, were measured. We then classified the hardness of each type. Mineral water had a hardness of 24 degrees TH, meaning it is classified as medium hard. Tap water had the highest hardness of 38 degrees TH, which makes sense, because it is known that Montpellier's tap water has a very high degrees TH. Lastly, the filtrated water through the membrane had a hardness of 15 degrees TH, falling into the soft water category. This indicates that the membrane did its job of separating out the magnesium and calcium ions, preventing them from entering the permeate, as there is a decrease in hardness when comparing the tap water and filtered water. The tap water had the highest conductivity, which indicates the high concentration of the dissolved ions, calcium, magnesium, aligning with its hardness classification. The permeate water had the lowest conductivity, which suggests that the nanofiltration process effectively removed the ions, which led to softer water. The mineral water's moderate conductivity aligns with its hardness level, classified as medium hard water. These results demonstrate the effectiveness of nanofiltration in reducing water hardness by removing calcium and magnesium ions, giving us softer water.